Today I'll talk to you about something that I've been working under the theme of for the last 10 years. And this is quantum error correction. And I'd like to phrase it in a way that in quantum systems, there's something that we cannot neglect or get rid of, which is noise. So if we have to build a quantum computer, we eventually have to make peace with noise. And I'll tell you about a specific way of doing this, making things resilient to noise in a way that it can actually be realized in real world. That is one way of saying it actually can be printed on a chip and made physical. So before we go on, I just want to thank people I worked with, things that are like fairly related to the theme of this talk. And in particular, the work that I'll be largely presenting today was done under the supervision of David Poulin, my PhD supervisor, who unfortunately is no more, and Nicola Delfos, who then was a postdoc in my group, now has moved to IMQ. Okay, so I want to start with a very general introduction. And in this talk, my aim is to actually convey what I know about quantum error correction at the high level and some details to you. So please ask any questions if you feel like something is hard to be followed. So let me pose the big question. As we kind of now hear probably a lot more from the industry and people who are building that how important quantum computers are, also from people who are doing more fundamental research about how they could potentially solve problems that are beyond the scope of classical computers. At the end of the day, we want to work with some abstraction that a quantum computer is nothing but a very elaborate quantum circuit. And what is the quantum circuit? It basically stores quantum information and manipulates it. So following the classical way of representing circuits, we have a bunch of wires and some boxes where we write what gates we apply. And these are operations. So what are these wires? We like to think of it as individual quantum systems. And in the language of quantum information, they're qubits. Okay. And these boxes are quantum gates. Now, this is a nice schematic, except that when we actually go and try to do this in a lab, it turns out that someone has turned on a microwave to heat their lunch in the next building, or there's a subway that's passing underneath the building. So these components are extremely sensitive to their environment, which means if I define like spin as my qubit, that means there's a magnet due to like some microwave radiation that's going on, and my spin actually deviates from its original configuration. At the end of the day, what I think is represented by the wire is actually not it.
So the components, do you mean locations?
Yes, locations and physical logical components like gates.
Okay.
So when we talk about like a real world computer, typically we have at right now to do like an interesting problem that's beyond supercomputers. We need something like 1 trillion components. So obviously we want very, very low probability of errors occurring, because we don't want such an elaborate effort to just go to waste because of some one error or a couple of them. Now, what is the solution? The solution in theory is actually given by a mechanism that says we cannot at the engineering level shield the system, but maybe at a software or at a logical level, we can work in the presence of noise. So this is quantum error correction. And in a picture, what is it in this language of wires and gates? It's like saying, let the qubit not be a single wire, but be a collection of wires, like a cable. This is pretty much like how we do it in the classical world. We just distribute our data, add redundancy. So in the quantum language, what do we mean by distributing the information? It's like building an entangled state. So we have some information that was originally encoded in physical qubits, now is encoded in a collective or an entangled state of many physical qubits. And that entangled state is what we call a logical qubit. Okay. Now, what we'll in a minute see what kind of entangled states, but these are special entangled states such that if individual physical components have an error, you can now give that information to a classical computer and it will reconstruct the entangled state. So like that, we actually preserve the information in the presence of errors. Okay, so with that kind of a high level description, let me quickly tell you what people are looking for in this entire process, right? At the end of the day, for someone who's building a device and adding this much overhead into the system, what do we want to know? Earlier, there was some kind of a mathematical model. Let's think of these errors as occurring with probabilities. There was some 10% chance of a qubit having an error. Now, after you have done this entire mechanism of replacing a qubit with a multi-qubit entangled state, what is the probability that the entangled state or the quantum information has an error after doing all this, right? So we normally represent it by graphically in this way, where for for any physical noise setting for any hardware, you have a point on the x-axis that says how much noise is there in the hardware. And the corresponding point on the y-axis says if we did quantum error correction with a particular way of storing information in entangled states, what is the noise that still remains in the logical information after doing the reconstruction, because the reconstruction is not perfect. Okay. Now, the nice thing about this scheme is that one can guarantee the bigger you make the entangled state, the better you get at suppressing noise on the logical information.
What do you mean by the bigger entangled state?
Yes. So ultimately, our qubit is made up of a system, a two-level system that has a 0 and a 1 as the basis states. Now, in this way, what I'm saying is that instead of calling 0 to be the state of a bare qubit, I'm assigning 0 to a multi-qubit entangled state. Like it can be some superposition of, say, 10 qubit states. So it can be something like
the degree of entanglement matters.
Yes, yes. So here, what I'm saying is that I'm saying instead of an entangled state with 7 qubits, now I have an entangled state with 14 qubits, which means I can afford to have more qubits have errors and still reconstruct the 14 qubit state because there are more symmetries in this.
So in case if you're making an entanglement, sorry, maybe in that case, you are applying some kind of entangling operations.
Yes.
Gate or something.
Yes. So to construct the 7 qubit state, I'm applying a circuit, starting with a single qubit state and some zeros, and I'm applying a unitary circuit to get the 7 qubit entangled state. For a 14 qubit, it'll be a bigger circuit. Okay. So as I keep doing this, I get better and better in terms of suppressing noise. And in fact, I can keep doing it and I can keep getting better. And eventually I'm going to reach some target that I wanted for my big algorithm, but at a massive cost. This case, I can say if I use something like 117,000 physical qubits per logical qubit, I can, for 18% physical noise rate, I can get something like 0.1% logical noise rate. But the question here is, how much of an overhead do you have to add to build an algorithm? And how better should you go on the hardware side? There should be some kind of a trade-off between these two. And we want to basically estimate these quantities because these are very important design parameters to actually build an algorithm. In other words, what we want to study in error correction is what are different architectures for writing logical states as entangled states of physical qubits, such that those architectures are easy to analyze in theory, What are we trying to analyze? We're trying to analyze what's the noise that persists after quantum error correction. We want to study it numerically because right now we can't build the device. We have to do classical simulations. And eventually we want to keep in mind that we have to do a physical realization. So they have to be friendly towards like adapting it into some existing many body systems. And eventually we want to know the performance before building it. We want to know what we can achieve. Okay, so I'm going to give you a very quick survey of what already exists, and then we'll go into the details of what this quantum error correction process itself is. What exists? So what do we want from an error correcting code? Of course, an error correcting code means we are specifying two entangled states. One represents 0 and one represents 1, and that's my qubit. Now, I had this pictorial thing with a logical qubit made of 14 physical qubits. Now, if I have to specify an entangled state of 14 qubits, the amount of information I need to write down to specify it scales exponentially because the number of basis states scale exponentially. So I want special entangled states where I don't have to communicate an exponential amount of information to specify it. That's one. The second is, of course, I don't want to add 100,000 physical qubits per logical qubit. I want to keep that overhead as low as I can. The third is, of course, I want it to be easily accommodated in experiments, which means at some point, like these things should be written down by Hamiltonians that have low body interactions. We'll come to that in a while. And we want efficient classical simulations of this entire quantum error correcting process. Okay. Of this quantum error correcting process. So right now we know a bunch of different strategies to do quantum error correction, and they all go by different names associated with quantum error correcting codes. One of the more studied ones are called surface codes. One of the most studied ones are surface codes. There are color codes, something that were originally started when quantum error correction as a field started, called concatenated codes. Now from the classical literature, we have things that are known as low density parity check codes and so on. And of course, random codes for proofs. Now, if we look for efficient descriptions, fortunately, all of them but random codes have good efficient descriptions. So that means we don't want to work with random codes.
We define as what is efficiently, computationally efficient.
Yeah, of course, of course. So what is this? What we mean here is that when we choose to describe a quantum error correcting code, we have to basically specify it. And how do we specify? We have to say what my logical qubit is. You have to say what is your 0 state and what's your 1 state. My 0 and 1 are they're entangled states of many physical qubits, like in this case, 14 physical qubits. To specify an entangled state, I need to convey amount of information that's exponential in the number of physical qubits. Why? Because there are so many there could potentially be so many basis states in the superposition.
Whenever it is in quality of.
Exactly. We don't want to spend something exponential. It has to be conveyed in polynomial amount of resources. Okay, so in terms of what gives minimum overhead, well, for surface codes, although it's not completely true, the overheads are still manageable with current architectures. For other codes like color codes, concatenated codes, the overheads are pretty bad in the sense that you can put in even infinite physical qubits and you will still get one logical qubit. With other LDPC codes, the overheads are good, but they're hard to study. Now, for experiments, it turns out that surface codes are actually quite good in terms of actually implementing it on a device. And concatenated codes are not that good. And for benchmarking, actually, importantly, it was kind of not completely known if there are very efficient simulation tools to study how surface code quantum error correction does behave on a real quantum computer. And this is something we'll touch on in this talk. And for other codes that are actually good, this is an open area of research. We don't yet know of good classical simulators. Okay, so now I want to, with that kind of introduction and provocation, I want to go into more details of what we mean by quantum error correction. We kept kind of hand waving and saying it's an entangled state. Yeah, sorry.
I'm sorry, I have a small question. So in the previous slide, could you explain again what the last point was? I got a bit, so benchmarking, what exactly are we referring to here? Because I thought if you have the algorithms, like we don't have guarantees for how well the algorithm decodes. Is that the issue, or
Yes.
how efficiently you can decode, or?
That's true. This is like benchmarking largely means like the decoding is at the backbone of the error correction strategy. So you're taking some information, some measurements from computer. For most of these good codes like LDPC codes, for instance, we don't know of good efficient decoders. Good in the sense that they perform well, and efficient in the sense that the complexity scales polynomially or preferably linearly in the size of the code.
I see. So people come up with like heuristic decoding algorithms, and
Exactly.
they look at how well they perform. Is that the okay?
Absolutely. The entire decoding field is almost always coming up with heuristics because the true optimum or the naive optimal decoding is again exponential time. Or we don't know if they're in the field or not.
I see. Okay, thank you.
Sure. Okay, so let's look at this in a more finer detail. What do we mean by quantum error correction and encoding? Okay, so let's take, I'm going to explain this with an example, with a concrete example. So let's take the idea of encoding one logical qubit into 7 physical qubits. What do we mean in this strategy? If we had information encoded into a single physical qubit, it's not good because noise can affect it. Now we are going to choose 2 states out of the space of all 7 qubit states. Call one as 0, call one as 1. Obviously, they have to be orthogonal to each other. Okay. Now remember that specifying these 2 states is generally hard because they're 7 qubit entangled states. Instead, I will indirectly say that I'm not going to exactly tell you what the state is, but I'm going to say that it's a +1 eigenvalue. It's an eigenvector with eigenvalue +1 of these 6 operators, M1 to M6. Okay. And let me know if you cannot see it. I'm happy to write it on the board. But okay. And then it's in my value. So I will write it on the board, but meanwhile we can just try to see what we can make sense out of this kind of a description. So one of the immediate things is, as you can kind of see vaguely, that these are all Pauli operations. So when I say 4x's, it's the Pauli matrix X tensor product with Pauli matrix X and so on, tensor product with 3 identities. So this is a 7 qubit Pauli matrix. And as you can see, we have 7 qubit state here. So this Pauli matrix, when I apply to a 7 qubit state, should give me exactly that 7 qubit state back if it is one of my 0 or the 1. Okay. Now, Now, what are the different eigenvalues this Pauli matrix can have? It can either have +1 or -1. And I'm just choosing +1. Now, I say it's not only this, but it should have exactly the same property simultaneously with this 7-qubit Pauli matrix also. And again with M3, M4, M5, and M6. Now, one thing we can immediately say from these operators M1 to M6 is that if they have to simultaneously have a common eigenvector, that means they have to commute with each other. Again, just because we'll be seeing it multiple times. So these are the 6 that I call M1. So these are all my 6 Pauli matrices for which I've indirectly said the states that encode my logical qubit should be a +1 eigenstate at the same time of all these 6 matrices. Now you can pick any 2 from here and you'll see that they commute. In particular, you can pick M1 and M4. And although X and Z anti-commute, you'll see that it anti-commutes even number of times. Okay. So the other observation is now you can say, are you even completely specifying the 2 states 0 1? And we can see that. What? Because these M1 to M6 have eigenvalues either +1 or -1. What happens if we take the set of all 7 qubit states and say, I only want to focus on states that have +1 eigenvalue with M1? You will exactly exclude half of the states because one half will have -1 and one half will have +1. Now your state space is 2 to the 6th dimensional. Now you'll introduce M2, and if it has to be +1 eigenstate of both M1 and M2, there are only 2 raised to 5 possible basis states. And now M3 and M6, and when you introduce all M1 to M6, you'll just have 2 possible states, basis states that are simultaneously +1 eigenstates, which means we have a qubit, which means this is all the information you need to specify the 0 and 1 states. Okay. Now let's see how that actually works in practice. Now let's say in the 7-qubit state, now it went through some noisy medium and there was some error. Okay. Error is nothing but some unknown operation. For now, we'll focus on just an unknown Pauli operation. Now let's say this is what we know, but this is normally not what an experimentalist would know, that there was a Z phase error on the 3rd qubit. Now, what could possibly be done? We know as an observer that the state has now gone to Z3 times this encoded state. Now, we know that to start with, it should be a +1 eigenstate of all this. Otherwise, it's not even a valid code state. So our first instinct would be to go and measure M1 to M6 and compute its eigenvalue or the measurement outcome. Now, this step in error correction is called error detection. Because it has +1 -1 eigenvalues, I can parameterize the eigenvalue as -1 raised to some binary outcome. And essentially, the binary outcome tells me the measurement outcome. Right? So measuring each M1 to M6 gives me one binary outcome. I can just write the whole thing as a binary string. That's the outcome of measuring everything I can. This is very important. In quantum mechanics, usually measurement is considered as collapsing the information. Here, it's a special type of measurement because these measurements originally actually preserve the state, the encoded states. So by measuring M1 to M6, you're not actually destroying the encoded information, but you're just checking if the new state is still in the encoded subspace. So now what happens is that because this is not an encoded state, it's neither 0 nor 1, we will naturally find that for some M1 to M6, the outcome of measuring that operator is -1 instead of +1, which means one of these SIs would have been 1 instead of 0. In other words, if we actually write it as a linear algebra equation, we have something like E on psi, and we are applying M. So for this to give minus E on psi, you can see that this can only happen if M and E anti-commute. Because M actually gets absorbed into psi. So if they anti-commute, anytime we see a 1 in this syndrome, we know that the error was unknown, but it actually, there was some non-trivial information, which is that it anti-commutes with a known operator M. Okay?
I reference you by adding ancillars to the.
Yes, absolutely. Absolutely. Yes, yes, yes. We will do the measurement by coupling with an ancillar. Yes. Okay, so now the natural next question is, now we have all the measurements. What can we say about this unknown error? And this, I mean, we cannot say precisely what the error was because multiple errors can give the same measurement outcomes. So we have to do some kind of a statistical inference where we have to say of all possible errors or Pauli operators that anti-commute, that have a specific anti-commutation relation based on the syndrome, which one was most likely? And this is what we call as decoding in quantum error correction. This is like, this part actually is just solved by a classical computer. And this is one part of a quantum computer that we can't really replace a classical computer. So the entire speed is actually the bottleneck for all the speed of a quantum computer is actually the decoding part. Okay, so the decoder is going to do some kind of inference and say, this is the Pauli error that is consistent with all the measurement outcomes. And this Pauli error is most likely. Now, how do I check? I will basically, because Paulis cancel themselves, I can go and reapply that Pauli error on the state. Now, if I reapply the Pauli error on the state, and I note that the Pauli error is nothing but the error that actually occurred, then I'm good. Then I've exactly undone what has occurred. There's a small subtlety. What if it's not exactly what occurred, but it's exactly what occurred times one of these harmless operators? Because including or not these harmless operators doesn't really change the encoded state. So if the error was Z3 or Z3 times M1, it has the same effect on this side. Right? So there's a small freedom there. We don't have to exactly guess what error occurred, but we can be wrong about the most likely one, but luckily if we are wrong by a factor of one of the M's, it's fine. But if that is not the case, if it was Z3 and we guess Z1, then the whole scheme has failed. Or if it's Z3 and we guess something that's Z3 times something that's not one of the M's, then the whole scheme has failed. So this is in principle how the whole error correction mechanism works. And in the way that I've described it, this is how a simulation would work. Okay. With that, now we understood with an example, what is quantum error correction all about? How do we specify a code? and how do we actually go about thinking about error correction. Now let me go to some more specialized type of codes. And what is specifying a code? More structured set of these operators, for which I'm looking for +1 eigenstates. And just for brevity, these operators are called stabilizers because they stabilize your state. Okay. And now the premise for looking for structure on these stabilizers is, as he pointed out, we have to measure them. And to measure them, there is a certain difficulty in measuring an operator depending on what that operator is. It's hard to do a 7-qubit measurement. Why? Because we have to couple 7 qubits on a system, and with main field couplings, it's going to be an extremely weak coupling. So we want to, whatever we measure, we want to keep it as small as possible. And now is where state surface codes will come into picture. And surface codes are a type of quantum error correcting code specified using stabilizers that was originally invented by Kitaev, and then for a few years it was kind of dormant, and then recently it really picked up after superconducting qubits became something that's achievable, and now very big industrial efforts like at Google and IBM, they have taken the path of building quantum computers using superconducting qubits with surface codes. Okay, so again, to specify a code, I need to specify stabilizers. How am I going to do that in surface code? I'm going to do something even more pictorial. I went from specifying a state to operators. And now I'm not even going to write the operators. I'm going to give you a picture where the operators are implicit. What? I'm going to specify something like a grid where I'm going to say, think of each edge in this grid as a physical qubit. Yeah. So in this 10 by 10 grid, you have 200 such edges. You have 200 physical qubits, right? Now, think of each vertex in this grid as specifying an operator, which is a stabilizer. What's that operator? It's precisely an X on all the edges that touch this vertex. Earlier we had this operator. Now I'm saying I won't write this explicitly. I'm just going to draw a vertex to represent this. And this is exactly a 4-body X operator, just like this. Right? I'm going to do the same thing with the faces. For the faces, I'm going to represent a Z-type operator, where it's 4 Zs on all the edges that border that face. Now, one of the first observations we did was we said, first of all, these operators, to have a common eigenstate, they have to commute. Earlier, we explicitly checked it. Now we can check it kind of geometrically. Why? Because if you take any vertex and any placket, the commutations actually matter when they share an edge. Right? And you'll see that any vertex and any placket share an even number of edges. There'll be even anti-commutations, which means all of these operators, one for each vertex and one for each placket, can potentially have a common eigenspace. Okay. Now, you may say, like, is this even physically possible? There are several nice realizations. For instance, you can think of this to be like an optical lattice with neutral atoms at the qubit sites. Or you can even think of like superconducting qubits at the sites and so on. Now, there's a nice condensed matter picture also hidden here, which is now you can say, when if it's a +1 eigenstate of all these operators, one for each face and one for each vertex, I can say the simultaneous +1 eigenstate is the ground state of this Hamiltonian. It's a commuting Hamiltonian. You can exactly solve it. Okay. Now, Earlier, we did like a counting argument where we divided the space into 1/2 each time we introduced a stabilizer. We can do exactly the same counting argument. How? What is the number of edges? Okay. In an n by n lattice, there will be 2n squared number of edges. Yeah. How many vertices will be there? N squared vertices. How many faces will be there? N squared faces. So total number of qubits is 2n squared. Number of X-type stabilizers that cut the thing into half is n squared, and number of Z-type stabilizers is also n squared. Which means if we look for a common +1 eigenstate, the dimension of the eigenspace is actually 2 to the 0, which means this is a unique eigenstate. We can't call this a qubit yet because there's only one state. It's like just having the 0. So we'll see in a minute how to fix this. There's multiple ways to fix it. But now we have a set of stabilizers that we can work with. Okay. Now you see that if I have to do a measurement ever, I only have to couple not only a small number of qubits, but things that are geometrically near each other. And in several hardware instances, this is actually much easy because I don't have to do swaps and stuff to couple it. Now let's keep the zero-dimensional space a little aside for just one slide. And now let's think about how convenient this way of representing a lattice to specify a code is. Now I can say there's nothing sacred about the square lattice. I can do exactly the same thing with a hexagonal lattice, where I can say the qubits implicitly stay on the edges. Okay. And if I look at the faces, the red faces here, they actually specify a Z stabilizer. I can look at the red vertices, or I can draw this dashed blue lattice and look at the blue faces. They're equivalent. They're dual of each other. Okay. If you only want to look at faces, you look at faces in red and faces in blue. If you're okay with looking at faces and vertices, you just forget about the blue. Just look for vertices and faces in the red. And they give you two types of stabilizers. Like M1 to M3 is one type, M4 to M6 is one type. Okay. Now these together describe a surface code. Okay. Now,
Sorry, so
okay,
can I ask a quick question?
Yes.
So I sort of forgot in the previous slide, how do we define a dual lattice given a lattice? We'd swap the edges.
Yes. Perfect. So how do we define a dual lattice? In a dual lattice, yeah, every face is replaced by a vertex, and two vertices corresponding to faces are connected if they share an edge. So if I can explain with this, you see like this red face is actually represented by a vertex in the dual graph, that is this dot. This red face is a vertex, that's this dot. Why are these two vertices connected? Because these two faces share this edge.
Right.
So,
sorry, the connection's a little bit choppy, but I'll ask you afterwards.
sure. So like in the square lattice, you can try to see what the dual lattice would be. And what would it be? So I put a vertex at the center of each square, and I'll connect those vertices if two of these faces share an edge. It'll again be a square lattice. It will just be something that's shifted diagonally to the southeast. Okay. But that's only for the square. For the hexagonal, the dual actually is a triangular lattice, and so on. But nevertheless, we can use the lattice and its dual to now specify our stabilizers. Okay. So now we talked about how a lattice can be used to specify a code. Now we can, there is no mathematical requirement to have this lattice on a plane. We can tessellate any surface. In particular, we can have this lattice on a torus. We can have this lattice in hyperbolic space. And for what is more viable, experimentally, we want to have this lattice on a chip. But having it on different manifolds actually leads to different error correcting properties, which we won't go into. Right? Okay, so let's come back to the problem that we kind of pushed under the rug for a couple of slides, which is the common +1 eigenspace is actually one-dimensional, which means there's only one state. Is zero-dimensional. Is actually there's only one state. Okay, how do we get rid of this in a very straightforward way? We just say, maybe I over-constrained the system. Let me just drop one constraint. And let me say it's no more a +1 eigenstate of this particular placket. Why this particular placket? There's no choice here, like you can drop anything. If it's no more a +1 eigenstate of this, what does it mean? It can be either +1 or -1 eigenstate of this particular placket. Now suddenly we have an eigenspace whose dimension is 2. Because the set of all n-qubit states that are simultaneously +1 eigenstates of everything but the thing in the question mark is actually 2.
The change it will make over will be in the encoding circuit. We have a qubit.
Exactly. There are two ways to think about it. So as you said, like you can encode. That's how you prepare the encoded state. Or like the encoded state is a +1 eigenstate of these stabilizers. So you can just take a random state, measure and post-select. Right? So you measure a stabilizer, you'll get +1 -1. You just throw it out if you get -1. You keep it if you get +1. It's a bad strategy, but conceptually what it means is that you choose not to measure this. That's all. Okay. So now we suddenly now have a qubit, a logical qubit encoded in this surface code. And it is a logical qubit because the counting argument says the eigenspace as dimension 2. Okay. Now you can kind of say what actually is the meaning of this thing that I didn't choose to measure, this Z operator. Now what it does is if you apply it to your entangled state, it actually takes the 0 logical state to the 0 logical state, but the 1 logical state to -1 logical state. So it's acting like a Z in the encoded space. Okay. Likewise, if you take this X, it's acting like an X in the encoded space. Now, importantly, you see that this Z operation actually commutes with all the stabilizers that remain, but it's not one of them. Likewise, this X commutes with all the stabilizers, but it's not one of them. Right? Which means if there are operators that commute with all the stabilizers, but are not one of the stabilizers, these apply logical transformations in the encoded space. Okay. Basically, what have we really done? If we forget the fact that there was a stabilizer code and so on, we specified a lattice with a hole. So you can think of it as specifying a stabilizer code with a punctured lattice. And there was nothing special about dropping this phase you could have said, why not drop a vertex? That's also a stabilizer. So you can do any combination of these. Each time you drop something, you allow for a factor of 2 in your encoded subspace dimension.
So my qubits are on the edges.
Yes.
So X on the logical X which you mentioned,
Yes.
it's those three. Now logical X and logical Z should entangle.
Yes.
Then over there, so the logical X is on the vertex. That means that it's on those four qubits.
So
One of the two.
exactly.
The X and Z are on one edge. The one overlap with them. So are they ambiguous?
Okay, it's not on the vertex, it's on the edge. So
The vertices are virtual, they don't exist. Like if you actually see the hardware, they're just qubits in free space.
I thought it's associated with the vertex.
No, the vertices are
side.
exactly. So, and that's a very good observation that the logical X and Z actually behave like Pauli X and Z in the sense they have to anticommute. So they do anticommute. So now I can generalize this. And what have I gotten out of adding this puncture? I earned one logical qubit. Now I can do this in many complicated ways. Now I can not only drop this face, but I can drop this edge, I can drop vertices. Geometrically, when I drop a placket, like here, you see that it looks like a smooth hole, the sense that there are no rough edges. Okay. So what I call when I drop a vertex is it looks like these edges are just like pointed and dangling. So this I call a rough hole. So a rough edge, a rough boundary and smooth boundary, I can have a hole that's partly rough, partly smooth. Anytime I make these changes, I earn logical operators. Okay. Now let me tell you what is so special about these logical operators. From nature's perspective, anything can happen in terms of an error. So if this actually does a meaningful operation on my encoded space, I don't want it to happen without my knowledge, right? That means these logical operations have to be such a way that they cannot spontaneously happen. Now, what do you mean by spontaneous? A single qubit can flip on its own, but the understanding is 10 qubits won't flip on their own. Why? Because noise is stochastic. So P is actually more likely than P raised to 10. Here, for a logical operation to happen on its own, the probability is roughly P raised to 4. Right? And you see that if I made the whole size of 2 plackets, it would have actually been P raised to 7. That's the perimeter of the hole. If I made the whole 3 plackets, the Z will actually be 1, 2, 3, 4, 5, 6, 7, 8. P raised to 8. But in hindsight, I will be reducing the X. Right? I can't make it very big. I have to be mindful of how close it is to the outer boundary also. So there is an intrinsic packing argument here, which is you want to put more logical qubits, but you want to do it in such a way that they're represented by punctures that are as big and as apart from each other. Now that's good for the simple picture of holes that look like this. Now for this, it's a little bit more complicated because you need to go and work out what the logical operators are each time you put holes. And now you need to look for that one problematic short logical operator because it constitutes an error that can happen reasonably likely just out of your knowledge. But nevertheless, one can do this and one can basically get rid of the problem that the encoded space had. There was no space to encode. Now you have a lot of space to encode. Okay, so now I want to essentially go and say like we saw how error correction, how to set up the surface code, how error correction in general works. We didn't see how it works for the surface code. Now I'll quickly mention how we encode qubits. In other words, this thing about like how we prepare this encoded state. We can do it using a circuit, or I'll show you another way of doing it, because this is actually a little more relevant to how some photonic companies and stuff they go about thinking about.
Here you puncture at random positions, right?
Yes, yes,
So do we know if we do some structured puncturing,
yes,
will we get more benefit?
yes, yes. As I said, like this. So there are two ways. One is, yes, for sure, if the outer lattice is known, there is definitely an optimal way to puncture. How? You want the punctures to be as far away from each other and as big by themselves. So you'll actually see using geometric arguments that square is not the optimal shape of a puncture. Why? Because you're wasting more space here than you're wasting space here. Right? Why? Because if you put a square hole, right? If you look at its distance to all the boundaries, they're not the same. Like, look at what is the distance between here and this boundary? It's 2 links. Okay? What's the distance between
This one.
yes? What's the distance between this and this? You can't go diagonal. You have to go like this. Okay, that's more. So in some sense, you could actually make more optimal use by making the hole bigger in that direction, right? So the more optimal thing is to put diamond-like holes for the square lattice. Now, what it is for hexagon is a little bit more involved. Okay, so how do we encode qubits? As one of you asked, like the basic principle here is to note that the encoded states are +1 eigenstates of the stabilizers, which means if I take any random state and measure this M1, I project onto either the +1 or the -1 eigenstate of M1. I can just post select on the +1 eigenstate. So I can keep measuring all of this. Now the question is, what state do I start with? Do I start with just a random state, or do I start with all zeros, all ones, identity, mixed state? What? The common choice for many other reasons is to start with a fixed entangled state that we call a cluster state or a graph state. What is a graph state? It's one unique state where you have plus on all the edges of a lattice, and the links are actually CZ gates. Right? So if you have a state like this, what you can now do is you can now start measuring these stabilizers by measuring X at the center and Z on the boundaries, and you'll actually project those 4 qubits onto the +1 eigenstate of the Z stabilizer.
So how did we start off? On the vertices we had state,
Yes,
and you said the links are
CZ, CZ.
Where is control? Where is the link?
For CZ, it doesn't matter. It's symmetric. Okay, so for CX, it matters. For CZ, it doesn't matter which is control, which is theta. So you actually apply this, and you can do this on any graph, not just square lattice. Now, once you've constructed the state, you can actually do single qubit measurements and project qubits onto the +1 eigenstate of the stabilizers. And basically, if you measure the central qubit in X, it turns out that just because of the property of the cluster state, these 4 circled qubits will be in a +1 eigenstate of Z. If you measure this central in X, these 4 will be in a +1 eigenstate of Z. And what you've actually done, if you rotate it 45 degrees, you have the surface code. And likewise, you can do the same thing for Z stabilizers, for X stabilizers. So in practice, this is a little bit of more kind of accelerating to what is done in practice. In practice, you would start with a cluster state, do those X measurements, initialize it in the +1 eigenstate of the X stabilizers. Now go to the dual lattice and do those X measurements again. Now it will initialize the +1 eigenstate of Z stabilizers. Now you keep repeating this in time. And at the end, after some time, you will actually have the +1 eigenstate of all the stabilizers. Therefore, you encode information. You prepare an encoded state. Now, this thing was actually proposed by Rossendorf, and the 3D lattice you get is called the Rossendorf lattice. Okay, so that was like a quick precursor on how encoding is done. Now let's come to the most important part of why surface codes, which is how do we do decoding? So in this toy example, we kind of brushed one thing under the rug, which is we said we measure this syndrome, all the commutation relation. We never said how to pick that operator that was most likely, that had exactly the same commutation relations as the measured syndrome. Now I'll show you how that picking becomes easier with surface codes. Okay, let's go back to the best way of conveying this information, which is through an example. Okay. I have the surface code. For now, you can imagine holes anywhere in this lattice. For now, let's not worry about where the holes are. Okay. For now, let's just worry about the fact that there are some qubits that have some unknown Z operation. There are some qubits that have an unknown X operation. Y is a product of these two, so we don't need to separately deal with Y. Okay. Now, what happens if there's a Z here on the encoded state? Now, if I measure all the stabilizers, what will I find? Especially if I measure this, nothing will happen because these states have not even changed. But if I measure corresponding to X's on this vertex, what will happen? This is an XXXX measurement. So this 4-body X actually anti-commutes with this Z. So this measurement outcome, that bit corresponding to that measurement outcome in this syndrome will be 1. What happens when I measure this stabilizer? Yes, it will be 0. Why? Because this 4-body X actually commutes. There are 2 Zs on either sides. But this one will again give me a -1, right? Same with X. What happens when there's an X here? This phase corresponds to a 4Z stabilizer. So Z, 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 Z. That gives me a -1 because now the state has changed to X applied on it and X anti-commutes. Same with this, and this. So at the end, as an experimentalist, what am I really seeing? I'm not seeing the error. What I'm seeing is that after measurements, and these blue dots represent measurements that were not consistent with my understanding of the encoded. In other words, if you kind of ask the reverse question as to what error could have happened, the most you can say is some error happened that actually is between these blue dots. You can't really say it's this because it could have been this, that can also create just these two, right? You don't know what happened in the middle. So in some sense, you only know the endpoints of the error as a chain. Right? Now, what does the decoder now have to do in this geometrical picture is, given these syndrome outcomes or given the endpoints of the error chain, you have to guess what the actual error chain was. The way we have seen this example, it almost looks obvious that if these are the endpoints, of course, this error is the only one that caused this pair of endpoints, right? For a minute, let's pause on that. Let it be obvious for now. And now, but we also acknowledge the fact that, for instance, in this case, the endpoints will be here and here, right? Now we'll ask what error caused this pair of endpoints. Well, you can say this, or you could say, well, I'm not really sure. It could also have been this, right? Or it could have been this. So there are multiple choices. But you'll say, like, stochastically, this is an error that flipped 2 qubits. The other possibilities involve error that flipped, let's say, 4 qubits or 3 qubits. So obviously, the one that flipped 2 qubits is more likely. In other words, you select errors based on a probability that roughly scales as though they are independent, which is p raised to the length of this error. Okay. Now, in the geometrical sense, what am I doing with these endpoints, with these blue dots? I'm just, any attempt to match them is specifying the error. If I match these two, what am I saying? I'm saying whatever edges I crossed in this matching, I'm basically saying, implicitly saying, my guess is that there's an error there. If I match this with this, I'm basically specifying a matching along this edge, and I'm saying this is the error that occurred. Geometrically now, decoding is starting to be cast as a problem where my syndrome is represented by pairs of endpoints, and I'm matching these endpoints. How am I matching? I want the length of the matched edges to be as small as possible. Okay. Now this is a very easy example, but here is a harder example. Now we are exactly seeing what an experimentalist would see. Now I'm not even telling you what the error was. Now, how will you match it? Now you may say, now I'm beginning to be more unclear because do I match this with this or this with this? In other words, what created these two endpoints? Did they come from the same error? Or this actually came, these two came from the same error and these two came from the same error? Right? So the question here is, I have a set of, if you now forget about the underlying lattice and just look at the blue dots, I have a set of vertices, connect them pairwise with edges such that the total length of all the edges is as small as possible. Why? Because all the edges together tell me one possible error that occurred on all the end qubits. Right? So now how is decoding done? We are already now seeing this take the form of a graph theory problem. What you would do is now you would build something called a syndrome graph. What is a syndrome graph? You say, look, I don't know what matches with what, but I'm going to take all possibilities. Okay, I'm going to say matching with this means you're guessing an error of length 2. Matching this with this means you're guessing an error of length 5. If you want to match this with this, it's an error of length 3. Match this with this, it's an error of length 7. I'll make all these connections available. Now I'll ask an algorithm, match points pairwise. When you match pairwise, the cost of that matching is the length of the edge that connects them. Okay, match it pairwise such that the total length of all the edges that are part of the matching is the lowest possible. Now this problem is exactly what's known as the minimum weight perfect matching in graphs. And this actually has a polynomial time solution. And this is given way before QEC was invented and stuff by this guy called Edmund.
Is the polynomial time, is it number of edges or?
Oh, yes, yes. So it's in the number of vertices here
Only vertices?
on the graph. Yes. It's,
Seems like number of edges are too many.
it's the number of, yes, you're right, you're right. What is the number of edges? It's actually, it's an all-to-all graph.
Yeah. And then prime.
Exactly, it's n squared. 10 squared edges. Okay. So you're right, it's actually, I was wrong. Like it's polynomial in the size of the graph. And the size of the graph is usually number of edges plus vertices. Okay. So because we know that the number of edges is actually n squared for n vertices, we can say it's polynomial in n. But it's not like a great polynomial, it's n raised to 6. Which means if we had a massive surface code and say 100 different pairs of defects, it will take time proportional to 100 raised to 6. That doesn't mean much, but now bringing in some engineering numbers, like if let's say you're trying to solve it on a laptop. So you have 100 raised to 6 operations to solve. That's 10 raised to 12 operations to solve. And your laptop clock speeds are like gigahertz. So this will actually take several years to do. You cannot afford to do a problem of this size. So although it's a polytime problem, it's not really in the regime of what can be solved. But okay, we made good progress. At least we can do 10 by 10 lattices. And in a regime where noise is actually sufficiently suppressed, you won't possibly have too many of these defects to start with, points to start. Okay, so with this, I'd like to kind of wrap up the discussion of the decoding problem, and I hope I've kind of conveyed to you how decoding is done and why surface codes, because decoding has a polynomial time solution. Now, of course, these blue dots, we only worried about the X errors. We can do exactly the same thing for the Z. Why? Because we can just go to the dual graph, and now the what was blue earlier, what was on the vertices earlier, now is on the faces. It's the same idea. We solve matching again on the dual graph. So we correct for X and Z independently. This we can correct for all errors. Now, in the beginning of the talk, I actually showed some kind of hand-drawn pictures as to how logical error gets suppressed as you add more overhead in this quantum error correcting code with respect to the physical error rate. These are actual simulation results. These are not just like some kind of schematic diagrams. Here you see exactly similar kind of plot. What do you see? You see, like, as you see different colors going down, you see surface codes larger and larger in size. And as in the x-axis, you actually see the probability of error per qubit. This is depolarizing. And like here you see different error mechanisms and so on. For people who want to go closer to the hardware, there are other models which more closely represent hardware, like amplitude damping. But this is why you can even make such plots with surface codes, because we have a polynomial time decode. Okay, so now I want to quickly tell you about this fact that, yes, we said polynomial time is good, but it's not great. We can't really still solve big problems. We can't decode big surface codes. Well, the solution, I'm not going to tell you something better than polynomial time for surface codes in the way it's presented, but for a special noise process. What is this noise process? These are called erasures. So there's a slightly different mechanism for noise at the physics level. So you can imagine like I'm encoding my qubit using the presence or absence of a particle, like photon. We have heard of like dual rail encodings. What is dual rail? I have two waveguides on my chip. If my photon is in the right waveguide, it's 0. If it's on the left waveguide, it's 1. So my qubit is two waveguides that track electromagnetic waves. Now, waveguides may not be perfect. There'll be some small imperfections. The photon may just escape the waveguide. Won't be trapped anymore. Which means I'm neither in 0 nor in 1. My qubit is lost. It's not like it had a random error. It's just not there. So, but the nice thing about these error processes is that when the qubit escapes, in principle, you can detect it. Because it's a photon, you can detect if you have single photon detectors and so on, you can actually detect where exactly the qubit escaped from. Okay? So these are error models where so far we've been saying like there's an unknown error and we don't know where it is. Here, you actually know where the error is. You just don't know what it is. It could have been an X, Y, or a Z, or it could have just completely taken into a mixed state where you can't really recover it. You have to replace it with a fresh qubit. Okay? But these are erasure noise. Now, see, from a decoding point of view, the hard problem is already solved. You know where the error is. You don't have to do matching and so on. But there's still a part of the problem that's left, which is you don't know what state these qubits were in before the error occurred, because you have to restore that state. Okay. Now, when is this a problem? It's a problem if you can't really detect what state it was in through measurements. Right? In other words, if you look at the error as a chain, and if it actually wraps around a hole, then you don't know what state it was in before. Because it could have been in the 0 state and nothing could have happened, or it could have been in the 1 state and a logical Z could have occurred, pushing it into a 0 state, but you still don't know what it was before. So in these, to correct these type of errors, to restore the system, you actually have to say, if my error is some chain, is there a logical operator that can be completely contained in this chain? Okay? And it turns out, I'm not going to show how, it turns out you can do this in linear time. This is a bit of an involved process. It involves computing what's called a homological dimension of a chain in a lattice. But I won't go into it. And it's there in this paper. Now we have a linear time solution, right? Now what we can do is we can really do benchmarking very fast because we can simulate the decoder very fast. Now here are some benchmarking results. These are for just simple 10 by 10 lattices. We have built a tool out of this linear time decoder. But here is the nice thing. Now you can use these fast benchmarking to study a system of 120,000 qubits. Now, if you use perfect matching to actually recover what error was, like we discussed before, for something of this size, now if you take an n raised to 6 complexity algorithm, you can kind of say back of the envelope that it takes several years to benchmark this because you have a very high complexity algorithm. Now with linear time, we can produce this entire plot in just 2 hours on a single CPU. Right? Because it's a linear time algorithm. So with this, I would want to kind of conclude this talk unless there's further interest to know more about how to do logical operations. I will actually just reserve that for questions. And I'll say like, we can also one of the other reasons for surface codes is certain logical operations can be done much easily directly on the encoded information. Like for instance, if we had this square lattice, and if I want to do a logical X, I want to take the 0 encoded state to the 1 encoded state. How do I do it? I don't want to apply C0 beats everywhere because C0s are actually bad in the sense that they can tie up a noisy qubit with a noiseless qubit. So I want to do operations that independently affect all qubits. These are called transversal operations. And for surface codes, you can actually show that many logical operations can be done transversely, which I won't go into right now. So with that kind of a general idea of surface codes, how quantum error correction works, how the decoder works, I want to wrap up this talk, and hopefully I've told you about what is quantum error correction at a more operational level. I've introduced surface codes, shown how to encode using this measurement-based picture with cluster states, and also told you about this linear time decoding strategy. With that, I'd like to end this. Thank you.